So this lecture is going to be looking at equilibrium and equilibrium reactions and how we can shift the equilibrium once it has been established. So equilibrium reactions are the forward and reverse reaction are taking place at the same rate. That is why we typically teach kinetics before we teach equilibrium, because of the interconnection between rate and equilibrium. So what you're going to see is in a chemical reaction, reactants on the left, products are on the right. You have what we call the forward reaction going from left to right and the reverse reaction going from right to left. So you will see in books and different resources, my worksheets and other people's worksheets, you could see the arrows drawn different ways. It just depends upon the application that you're looking at. But please look at this last example here. If I show the arrow is more predominant going from left to right than it is going from right to left, that means the forward reaction is more preferred or more favorable. So that is something that you might see. But again, an equilibrium reaction does not mean equal. It means the rate is the same. And hopefully you saw with that game that we had you play with collisions to kind of get a sense of that. So the only way we can change a chemical reaction is by changing what we call factors, okay? And so this has to do with something called Le Chatelier's principle. And I apologize for any of you that have a French background. I always say this one wrong, so I call it Le Chat. I apologize to everybody. But what this has to do with is equilibrium reactions. So if I apply stress to an equilibrium, the stress will try to be relieved, okay? So if we are under stressful conditions, we try to alleviate stress. Maybe we have a bad day at school. So we try to alleviate stress, hopefully in a positive way, by taking a walk or talking to a friend or taking 5 minutes to kind of de-escalate the situation. So we are going to be talking about stressing and equilibrium. Okay, so there are 4 different stresses or factors that we are going to be talking about. We have temperature, of course. We have adding a catalyst. We could change the concentration. So CO and C is concentration. And then we can also change pressure of an equilibrium, but this can only apply to gases only. So I'm going to go through each one of these factors and describe how that changes the equilibrium. So I'm going to start with concentration. Okay, I'm going to start with concentration. So if I take a look at concentration, I have this equilibrium. Okay, so these are my reactants, these are my products. Since these are reversible reactions, we do need to kind of keep that in mind. So what happens if I add H2CO3, which is a reactant? So if I add a reactant, think of it like you're making cookies at home. If I have more flour, more sugar, more anything, I could then make more product. So when I add more reactant to this equilibrium, it's going to make more product. Okay, so we're going to make more product. So what that means is I am shifting it to the right. Okay, so what we're going to talk a lot about in Le Chat is shifting the equilibrium to a certain direction. Okay, so we are adding H2CO3. I am essentially adding more reactant. I make product. Okay. If I happen to add CO2, so that means I am adding product, okay? So I'm adding it to the right-hand side of this equilibrium. So if I add it to the right-hand side of this equilibrium, because it is a reversible reaction, I'm adding more CO2. It's going to shift it to the left. So I'm going to make more reactant, okay? So I would say that this shifts left. Okay, because these are reversible reactions, I could add to either side, and what it will try to do is alleviate that stress. So anytime I'm adding, what I'm doing is changing the concentration. So if I'm changing the concentration, I'm stressing this equilibrium. So it's going to try to alleviate that stress. So in a general rule, anytime I add reactant, I'm going to shift to the product side. Anytime I add product, I'm going to shift to the reactant side. That's the general rule for anything in terms of an equilibrium, okay? But besides adding things, I could also remove things from an equilibrium. So again, back to this equilibrium. What if I removed H2O? So this could be mechanically, meaning I could dry it. I could take that sample out by extracting it. So whatever that happens to be. When I want you to think about removing something, okay, that means I'm lowering the concentration. So I'm going to write a down arrow to show that I'm reducing the concentration of CO2. However, I could do that. I could also put a chemical in there to remove the water. So if I'm removing the H2O, okay, that's a product in this equilibrium. I want you to think about digging a hole. Okay, so I'm digging a hole in this equilibrium. So I'm taking away the H2O, and it doesn't like the fact that I'm removing it. So this equilibrium tries to fill up that hole, okay? It tries to make more of that H2O because that hole has been made, okay? So think about digging a hole, okay, when I'm removing. So what happens is this equilibrium tries to make it up by making more product. So that means I am shifting it to the right. I'm shifting it to the right, okay? So that is how removing a product affects an equilibrium. What if I removed the reactant? Okay, so let's go to the reactant side. Again, I'm digging a hole. So since I'm digging a hole on the left-hand side, it doesn't like that. It wants to fill that hole back up. So what it's going to try to do is it's going to take the CO2 and the H2O and make it back into H2CO3 to alleviate that stress, okay? So I'm going to end up shifting it to the left. So I'm going to make more reactant, so I am saying I am shifting it left, okay? And again, you could just draw in the left pointing arrow. You will see that in further notes here. So in general, if I remove the reactant, I'm going to shift towards the reactant side. If I remove the product, it will shift towards the product side. And this has to do with what a chemist figured out, Le Chatelier, again, I apologize, the system will always shift to reestablish the equilibrium. And if you go back to that collisions game that you played, it showed you how if I introduced something or took something away, you might have seen that the equilibrium is reestablished, it's at a different level, but it's still a new equilibrium has been done. So that is the hard one, okay? The rest of it should follow, okay? So the next one we're going to talk about is temperature, okay? So if you understand concentration, this will make perfect sense. So here is my equilibrium, and I'm now putting heat in the equation. So heat is on the product side, okay? Heat is on the product side. So this is back to our thermo days from first semester a long time ago. Since the heat is on the product side, please remember that this is an exothermic reaction. If heat was over on the left, this would be an endothermic reaction. So if I add heat to this exothermic reaction, I'm essentially adding product. So write down I'm adding product. So what happens if I add product to this equilibrium? Well, it doesn't like that added stress, so it's going to try to shift to alleviate that stress. So it's going to try to make more reactant. So it's going to shift it left. Same idea with removing heat, okay? Let's say I'm putting it in an ice bath, okay? So I'm digging a hole. Adding heat's easy, okay? I could say I put it on a hot plate. That's easy to understand. But if I'm removing heat, so if I have this reaction taking place in a container and I put it in an ice water bath, I'm removing the heat. So the heat is going down in that case. So that means I need to make more product to fill up that hole, okay? So that means it's going to shift right. Going to shift right. So in general, exothermic reactions, if I add heat, it will always shift to the reactant side. If I remove heat, it will always shift to the product side. Likewise, endothermic is the exact opposite. So please note heat is going to be here. Here's my reactant, and I go to product. Okay, so if heat is over here, if I add heat, it will shift to the product side. So heat is on the reactant side, so I'm increasing that. It's going to alleviate that by shifting it to the right. If I'm removing heat, I'm digging a hole on the left-hand side. It doesn't like that, so it's going to shift it to the reactant side. So again, think of shifting to the product as shifting it right, shifting to the reactant as shifting it left. So we're going to use both of those to kind of describe what is taking place. All right, so two more, okay? One is pressure, okay, and the other is a catalyst, okay? Now pressure, good or bad news, is this only applies to gases. So what you have to be aware of in a chemical reaction is what is your state of matter, okay? What is your state of matter? So these all have gases, okay? So how many moles of gas do I have on the left? I have 1 mole of nitrogen and 3 moles of hydrogen. So I have a total of 4 moles of gas on the left. How many moles of gas do I have on the right? I only have 2. So what is happening in an equilibrium? This is all taking place in the same container. So keep that in mind when we're talking about any of these shifting of equilibriums. If I increase the pressure, that's an increased stress. Okay, so I have 4 moles and 2 moles bouncing around in an equation. If I shift to the side with less moles, that means there's going to be less pressure. Well, what is pressure? If I have a container with a bunch of gases in it, okay, the more gas I have in there, the more pressure is going to build up because it's hitting the sides of the container and hitting each other. Okay, so that buildup of pressure needs to be alleviated. So what's going to happen is I'm going to shift to the side with fewer moles. And that is a general rule for all gas reactions. If I decrease the pressure, generally that means I am increasing the volume. So if you want to put volume over here, if I decrease the volume, and you might have seen that in the collision game, you can increase the pressure just by changing the volume that it's in. If I increase the volume, I am decreasing the pressure because the gas particles have more places to go. I will then shift to the side with more moles if I decrease pressure in an equilibrium situation. So if I look at this particular situation, 4 moles versus 2 moles, if I increase the pressure, I'm going to shift to the side with fewer moles. So you have to look at the balanced chemical equation, and you're looking at the stoichiometry. Okay, and you're looking at the gases only. This one happens to be all gas, but when you look at a chemical reaction, you need to know how many gas particles you have. So think of it like a particle picture. So I have 4 circles versus 2 circles in a box. If I increase the pressure, I want to go to the side with fewer moles. So I want to make more NH3 in this equilibrium than I want to be on this side. So that means it's going to shift it right. If I have, because that is the fewer moles of 2 moles of gas, okay? If I decrease pressure, I'm going to shift it to the side with more moles. Well, how many moles do I have on the left? I have 4 moles, okay? So it's going to shift it to that side. So increasing pressure means I'm going to make more product. I'm going to make more NH3. If I decrease the pressure, I'm going to make more reactant. So it means all the same thing. It's either left or right. Right is always product, left is always reactant. And finally, the one that is influential in terms of the rate is a catalyst. So I will not shift the equilibrium either left or right. You are going to say no shift if you have a catalyst, okay? You only change the rate of the reaction. So that forward and that reverse reaction goes a little faster with a catalyst, but you do not change the overall equilibrium. You will just get to equilibrium faster. That is what's changing with a catalyst.